Good day everyone. My name is Miles D. Kaasi. Our topic is all about the development of mathematics, a historical overview modern period. And the subtopic that I will be discussing is all about the non-Euclidean geometry and the problems in the foundation of mathematics.
Good day everyone, my name is Aliyah M. Abdullah and the subtopics that I will be discussing is all about the modern algebra and number theory and the birth of set theory.
Good day everyone, my name is Raufa A. Kamid. Our topic is all about the nature of mathematics. The subtopic that I will be discussing is what is mathematics and what do mathematicians do?
Good day everyone, I am Benjamin D. Mabang. My subtopic is about mathematics is invented or created.
Good day everyone. I am Bayasmin Panangilan. Our topic is all about issue and aspect, and I will be discussing the concept and the rule of the proof.
Good day everyone. My name is Eliza A. Ali. The subtopic that I will be discussing is all about infallibility and certainty in mathematics.
The development of mathematics, a historical overview, modern period. First, we will be talking about non-Euclidean geometries. It all started with Euclid. So, Euclid in 325 BC to 265 BC was a Greek mathematician best known for his treatise on geometry, the Elements. This influenced the development of Western mathematics for more than 2,000 years. In about 300 BC, Euclid wrote the Elements. So, in these Elements, Euclid stated 5 postulates on which he based all his theorems. And these 5 postulates are to draw a straight line from any point to any other, to produce a finite straight line continuously in a straight line, to describe a circle with any center and distance, that all right angles are equal to each other. The 4 postulates that I've mentioned are all Euclidean geometry. But the 5th postulate is non-Euclidean geometry, which is this, that if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. So, as you can see in the diagram, there are 2 lines that are drawn which intersect the third line in such a way that the sum of the inner angles on the same side in that P and Q angles is less than 2 right angles, which is 180 degrees. Then the 2 lines inevitably must intersect each other on that side if extended far enough. That A and C in the diagram, it will intersect at some point if it's extended far enough. This is equivalent to parallel postulates. However, conclusions drawn from the postulates are very controversial, for they don't all apply on 3-dimensional or curved geometries, also known as non-Euclidean surfaces, such as conical, spherical, cylindrical, and hyperbolic surfaces. The 5th postulate is different from the other 4. As you have heard it a while ago, it did not satisfy Euclid and he tried to avoid its use as long as possible. When were non-Euclidean geometries discovered? It was discovered in 19th century. These geometries arose in the 19th century when several mathematicians working independently explored the possibility of projecting Euclid's parallel postulate. The following mathematicians that I would be mentioning are traditionally associated with the discovery of non-Euclidean geometries. So first, we have Carl Friedrich Gauss in 1777 to 1855, a German mathematician and physicist who made significant contributions to many fields in mathematics and science, the first to discover the non-Euclidean geometry but unknown. He began to work on the 5th postulate in 1792 while only 15 years old. The first person to really come to understand the problem of the parallels was Gauss. He began to work on the 5th postulate in 1792 while only 15 years old, at first attempting to prove the parallels postulate from the other 4. By 1813, he had made little progress and wrote, "In the theory of parallels, we are even now not further than Euclid. This is a shameful part of mathematics." However, in 1817, Gauss had become convinced that the fifth postulate was independent of the other four postulates. He began to work out the consequences of a geometry in which more than one line can be drawn through a given point parallel to a given line. Perhaps most surprisingly of all, Gauss never published this work but kept it a secret. The next mathematician was Janusz Bolyai or Johann Bolyai in 1860. Gauss discussed the theory of parallels with his friend, the mathematician Farkas Bolyai, who made several false proofs of the parallel postulate, and Janusz Bolyai is a son of Farkas Bolyai. Farkas Bolyai taught his son Janusz Bolyai mathematics, but despite advising his son or told his son don't waste 1 hour's time to solve on that problem of the fifth postulate, but Janusz Bolyai did work on the problem. In 1823, Janusz Bolyai wrote to his father saying, "I have discovered things so wonderful that I was astounded. Out of nothing I have created a strange new world." He explored what would happen if Euclid's fifth postulate was not true. However, it took Bolyai a further 2 years before it was all written down, and he published his Strange New World as a 24-page appendix to his father's book. The next mathematician was Nikolai Lobachevsky in 1792 to 1856. In 1829, Lobachevsky also published a work about replacing the fifth postulate. The postulate, there exist two lines parallel to a given line through a given point not on the line. French version published in 1837, which brought it to the attention of Europe. Neither Bolyai nor Gauss knew of Lobachevsky's work, mainly because it was only published in Russian in the Kazan Messenger, a local university publication. Lobachevsky's attempt to reach wider audience had failed when his paper was rejected. In fact, Lobachevsky fared no better than Bolyai in gaining public recognition for his momentous work. He published Geometrical Investigations on the Theory of Parallels in 1840, which in this year, in its 61 pages, gives the clearest amount of Lobachevsky's work. The publication of an account in French in Crill's journal in 1837 brought his work on non-Euclidean geometry to a wide audience, but the mathematical community was not ready to accept ideas so revolutionary. Next mathematician was John Playfair in 1748 to 1819. He worked on geology, physics, and geometry and studied at the University of St. Andrews. His best-known contribution to mathematics is his form of Euclid's parallelism, axiom. Playfair's axiom, given a line and a point not on the line, it is possible to draw exactly one line through the given point parallel to the line. Although known from the time of Proclus, this became known as Playfair's axiom after John Playfair wrote a famous commentary on Euclid in 1795 in which he proposed replacing Euclid's fifth postulate by this axiom. Next was John D'Alembert in 1717 to 1783. He was a French mathematician who was a pioneer in the study of differential equations and their use in physics. He studied the equilibrium and motion of fluids. Elementary geometry was by this time engulfed in the problems of the parallel postulate. D'Alembert in 1767 called it the scandal of elementary geometry. Next mathematician was Bernhard Riemann. In 1826 to 1866, he was a French mathematician who was a pioneer in the study of differential equations and their use in physics. He created spherical or Riemannian geometry. In geometry, the Riemann sphere is the prototypical example of a Riemann surface and is one of the simplest complex manifolds. Riemann briefly discussed a spherical geometry in which every line through a point, for example P not on line AB, meets the line AB. In this geometry, no parallels are possible. Riemann, who wrote his doctoral dissertation under Gauss' supervision, he gave an inaugural lecture on June 10, 1854, in which he reformulated the whole concept of geometry. which he saw as a space with enough extra structure to be able to measure things like length. This lecture was not published until 1868, 2 years after Raymond's death, but was to have a profound influence on the development of a wealth of different geometries. In the Riemann type of spherical geometry, lines have no, or more precisely, two imaginary infinitely distant points. The properties of Riemann. So as you can see in the diagram, the lines are great circle. Angle sum of triangles increase as the area increases. There are no parallel lines.
And now, let's proceed to modern algebra and number theory. Modern algebra and number theory are the two oldest fundamental branches of mathematics that are at the very center of mathematics even today. Algebra includes the study of structures of solution sets of algebraic equations, structure of permutations, combinations, and transformations. Number theory is mainly the study of integers, especially prime numbers. Integer are rational solutions of a system of polynomial equations in one or more unknown is a part of number theory that goes by the name of arithmetic geometry. In addition, abstract algebra and number theory are broad areas of mathematics which formalize intuitive notions of symmetry and which explore properties of integers and other closely related number systems. Modern algebra is also called abstract algebra, a branch of mathematics concerned with the general algebraic structure of various sets such as real numbers, complex numbers, matrices, and vector spaces, rather than rules and procedures for manipulating their individual elements. During the second half of the 19th century, various important mathematical advances led to the study of sets in which any two elements can be added or multiplied together to give a third element of the same set. The elements of the sets concerned could be numbers, functions, or some other objects. Bartel van der Waerden, 1903-1996. He was a Dutch mathematician, best known for his modern algebra textbook. He also wrote an algebraic geometry, topology, number theory, geometry, combinatorics, analysis, probability and statistics, and quantum mechanics. His historical writings include Ontwakkendi, Wetenschap 1950, which was translated into English as Science Awakening 1954, Geometry and Algebra in Ancient Civilization 1983, and A History of Algebra 1985. Francois Viet, a French mathematician known as the father of modern algebraic notation. His substitution of letters to mark unspecified or unknown number quantities is recognized as the beginning step in the creation of the algebraic system. Évariste Galois, 1811-1832. He was a French mathematician who produced a method of determining when a general equation could be solved by radicals and is famous for his development of early group theory. He ingeniously solved the classical problem of algebra by introducing something called Group as a set with identity and invertible element which can be associated. Groups: a set G on which a binary operation is defined between elements within the set is called group. If following conditions are satisfied, the group is closed under operation closure property. If A and B are elements of set, then C is equal to A multiplied by B also belong to the set. And then the number 2, the operation multiplied is associative, and etc. Fermat's interest in number theory. Fermat's interest in number theory was fostered by the works of Diophantus. At this time, the only sources on number theory were Diophantus' arithmetic and books. Ironically, Fermat meant to revive old classical mathematical traditions, but he actually ended up laying the foundation for a new modern tradition. Descartes' rule of signs in algebra, rule for determining the maximum number of positive real number solutions of a polynomial equation in one variable based on the number of times that the terms are arranged in the canonical order from highest power to lowest power. For example, the polynomial x raised to the power of 5 plus x raised to the power of 4 minus 2x cubed plus 2x squared minus 1 is equal to 0. And now, let's proceed to the birth of set theory, a branch of mathematics that investigates sets and their properties. A set theory provides a foundations for mathematics, and in the late 19th century, the mathematician George Cantor created and developed a mathematical theory of sets. George Cantor, 1845 to 1918. George Cantor was a Russian-born mathematician who can be considered as the founder of set theory and introduced the concept of infinite numbers with his discovery of cardinal numbers. He also advanced the study of trigonometric series. Zeno of Elea, 419 BC to 425 BC. Zeno of Elea was a Greek philosopher famous for posing so-called paradoxes which challenged mathematicians' view of the real world for many centuries. Zeno of Elea, and around 450 BC, with his problems on the infinite, made an early major contribution. By the Middle Ages, discussion of the infinite had led to comparison of infinite sets. In 1874, Cantor published on a characteristics property of all real algebraic numbers, which formally marked the birth of set theory, and because of this, George Cantor was considered the father of set theory. And in 1885, Cantor continued to extend his theory of cardinal numbers and of order types. He extended his theory of order types so that now his previously defined ordinal numbers became a special case. In 1895 and 1897, Cantor published his final double treatise on sets theory. It contains an introduction that looks like a modern book on a set theory defining set, subset, etc. Also, Cantor proves that if A and B are sets with A equivalent to a subset of B and B equivalent to a subset of A, then A and B are equivalent. Bernard Bolzano, 1781 to 1848. Bernard Bolzano successfully freed calculus from the concept of the infinitesimal. He also gave examples of one-to-one correspondences between the elements of an infinite set and the elements of a proper subset. Leopold Kronecker, 1823 to 1891. Leopold Kronecker's primary contributions were in the theory of equations. He made major contributions in elliptic functions and the theory of algebraic numbers. He only accepted mathematical objects that could be constructed finitely from the intuitively given set of natural numbers. Richard Dedekind, 1831 to 1916. Richard Dedekind's major contribution was a redefinition of irrational numbers in terms of Dedekind cuts. He introduced the notion of an ideal in ring theory. Dedekind was working independently on irrational numbers, and Dedekind published Continuity and Irrational Numbers.
Problems in the foundation of mathematics. In this slide, it discusses the problems in the foundation of mathematics. The foundation crisis is a celebrated affair among mathematicians and has also reached a large non-mathematical audience. A well-trained mathematician is supposed to know about the viewpoints, and these are logicism, formalism, intuitionism, and the Gödel's incompleteness. So first, the early foundation of mathematics. Evidence that in 1899, Hilbert David endorsed the viewpoint that came to be known as logicism. It was the basic concept of mathematics and are definable by means of notion. Historically speaking, logicism was a neat intellectual to the rise of mathematics and particularly to the set theoretical approach and methods. They also said that the theories are of natural and real numbers can be derived from set theory. Dedekind approach in 1871 to algebraic number theory, his set theoretical definition of number fields and ideals, and the methods by which he proved results such as the fundamental theorem of unique composition. But the influential algebraic chronicle complained that Dedekind proof do not enable us to calculate. His views were that this abstract way of working made possible by the set theoretical method and by a concentration of the structures involved was to remove from an algorithm treatment called constructive methods. In around 1980s, Hilbert's work on invariant theory led to a debate about this purely existential proof of another basic result, the basis theorem, which states that every ideal is a polynomial ring is finitely generated. This early foundational debate led to gradual clarification of the opposing viewpoints. Cantor's proof in set theory also became quite essential example of the modern methodology of essential proofs. Around 1900, Cantor's continuum problem question in set theory, and with the problem of whether every set can be well ordered, his second problem amounted to establishing the consistency of the notion of the set R of real numbers. The problem shows that R can be well ordered. 2.1 Paradoxes Consistency. Comprehension principle is the set of all real numbers. Corresponding to the property of being an ordinal, there is the set of all ordinals. The principle was thought of as a basic logical law. Zermelo-Russell paradox shows that the comprehension principle is contradictory, and it does so by formulating a property that seems to be as basic and purely logical as possible. Number 4. Gödel's and aftermath. Extremely ingenious development of mathematics allowed Gödel to prove that systems like axiomatic set theory or Dedekind piano arithmetic are incomplete. That is, there exist propositions P formulated strictly in the language of the system, such that neither P nor negative P is provable of the system. In the end, the debate made it clear that mathematics and its modern methods are still surrounded important philosophical problem. But when it comes to laying out the bare beginnings, philosophical issues cannot be avoided.
The nature of mathematics. What is mathematics? The word mathematics comes from the ancient Greek and it is derived from the word mathema, meaning that which is learned. A mathematics is the science that is concerned with numbers and their properties, relations and operations, and with shapes in space and their structures and measurement. Mathematics is a fundamental part of human thought and logic, and integral to attempts and understanding the world and ourselves. Mathematics provides an effective way of building mental discipline and encourage logical reasoning and mental rigor. Mathematics is the science that deals with the logic of shape, quantity, and arrangement. Math is all around us. In everything we do, it is the building block for everything in our daily lives, including mobile devices, computers, software, architecture, ancient and modern, art, money, engineering, and even sports. It is not uncommon for people to wonder what relevance mathematics serves in their daily lives. In the modern world, math, such as applied mathematics, is not only relevant, it is crucial. Applied mathematics covers the branches that study the physics, biological, or sociological world. What do mathematicians do? Mathematicians use high-level mathematics and technology to develop new mathematical principles, understand the relationship between existing principles, and solve real-world problems. Mathematicians typically do the following: expand mathematical knowledge by developing new principles. Mathematics is one of the oldest and most fundamental sciences. Mathematicians use mathematical theory, computational techniques, algorithms, and the largest computer technology to solve economic, scientific, engineering, and business problems. The work of mathematicians falls into two broad classes: the pure mathematics and the applied mathematics. These classes, however, are not sharply defined and often overlapped.
The study of mathematics as a demonstrative discipline began in the 6th century BC with the Pythagoreans, who coined the term mathematics from the ancient Greek mathema, which means subject of instruction. So let us move on to the next. Mathematics is a human construct. The only reason mathematics is admirably suited to describing the physical world is that it was invented to do just that. It is a product of the human mind, and we make mathematics up as we go along to suit our purposes. The fact that 1 plus 1 is equals 2, or that there's an infinite numbers of primes, are truth about reality that held even before mathematicians knew about them. As such, they are discoveries, but they were made using techniques invented by mathematicians. So, the world is made of math. Math is both a product of invention and discovery, meaning it is also a product of the human mind. Generally, concepts in math are invented because human thirst for innovation. Math slowly discovered over thousands of years with the help of thousands of people. We want to make our lives easier and more convenient, which is why we keep on upgrading existing concepts through invention. That will be all. Thank you.
The concepts and rule of the proof. Infallibility in mathematics refers to the idea that mathematical proof and statement are absolute and certain. It is the belief that mathematical truth is objective and that mathematical proof are rigorous and valid.
When we say infallibility in mathematics, it refers to the idea that math proofs are rigorous and valid. This means that once a mathematical proof is accepted as valid, it is considered to be true and certain and cannot be disputed or challenged. In other words, So, these are several issues and aspects that call into question the infallibility of mathematics. Number 1, the existence of different mathematical systems. Each mathematical system has its own set of axioms and rules, and different systems may lead to different conclusions and proofs. This raises questions about the absolute certainty of any one system. Number 2, the use of unproven assumptions or axioms. Many mathematical proofs rely on assumptions that may not be rigorously proven, and thus the proof built on them is only as certain as the assumption itself. Number 4, mathematical intuition. The concept of mathematical intuition, which is the ability to sense the truth or falsity of a mathematical statement without a formal proof, raises questions about the objective nature of mathematical truth and the role of subjectivity in mathematical certainty. Number 5, human error. As with any field that is based on human reasoning and understanding, there is always the possibility of human error in the proof, calculation, or communication of the mathematical knowledge. Number 6, the use of computers to prove mathematical statements. The use of computers to prove mathematical statements raises questions about the reliability and certainty of such proofs, as the complexity of the proof can make it difficult to understand or verify. While certainty in mathematics refers to the idea that mathematical proofs and statements are true and can be relied upon as accurate and unchallenged, a statement or proofs considered certain when it is accepted as true based on rigorous reasoning and evidence, and is not subject to doubt or error. In mathematics, certainty is often associated with the concept of mathematical